Okay. Hi, everybody. First of all, I would like to thank the organizers for giving me the opportunity to come here and to tell you about the work we have been doing recently in Barcelona at the... This is nicer. This is too large. Well, anyway, so this is, I would like to present you today the work we have been doing recently at the Quantum Matter Simulation Group at Universitat Politècnica de Catalunya in Barcelona, which has been mostly done by Adrián Macia, which is the PhD student we have, and by myself, Professor Jordi Boronat, and some parts of the work have also been done in collaboration with Robert Zillig and Diana Hufnagel from the University of Linz in Austria, and also with Gregoria Strakarczyk, which is our colleague, also the Quantum Simulation Group in Barcelona, who will be giving a talk in the next week, I think. Okay, the outlook of the talk I'm giving is more or less this. I will first tell you about the details of the dipolar interaction, which is a subject of recent study in ultra-cold gases since less than 10 years ago. This is right now a hot topic. Then, since that emerges from the field of ultra-cold Bose gases, where the situation is always that they analyze dilute systems, we will first focus on how to describe the system at low densities and try to search for universal properties in equation of state as it happens in many other systems. For that, we will be doing Monte Carlo calculations, mostly Monte Carlo. That's the reason why we are here. And for doing that, we need to build up first a wave function, which we will try to build in an analytical way, more or less. A trial wave function that will be done more or less analytically. Once we have that described, we will go to the high density regime and then look for special effects of the induced by the anisotropy of the interaction into the system. We will then move into the description of the density response function, and finally try to say something about what the phase diagram of the system is. Okay, so let's start with the dipole interaction. So dipole interaction is essentially this one. We have two particles, two dipoles. We have a dipole moment P1 and P2, and the interaction takes terms between P1 and P2, and also P1 times the distance, P2 times the distance. And these terms are what bring the anisotropy of the interaction, because it's not just that particles are at a certain distance, but also the orientation between the dipolar moments and the position vector is relevant. In ultra-cold gases, there are two types of dipolar systems that have been analyzed or are currently being analyzed, which are the magnetic dipoles and the electric dipoles. Magnetic dipoles were the first ones to be studied in this ultra-cold gas business, and that started with chromium-52. Nowadays, this has improved in the sense that chromium is not very neat, in the sense that the dipolar interaction is also mixed with a two-matter interaction, and it's not clear that the dipolar interaction is dominant. Okay? But recent experiments with systems like dysprosium or erbium have shown very much stronger dipolar effects because of the magnetic dipole moment there is more important, and also the mass of the particles is larger. On the other hand, there is big hope on getting strong dipolar effects in polar molecules which have electric dipoles. Somehow you can see that in this table. You see the coupling constant in the interaction somehow, no? The constant in the interaction for a magnetic system is proportional to the square of the magnetic moment, while in the case of the polar molecules or electric dipoles, it's proportional to the square of the electric dipole moment. Here we have, for different systems, like rubidium, for instance, which has a minimalistic magnetic dipolar moment, we see that this constant here, which is the ratio, is proportional to the ratio between the characteristic length scale of the dipolar interaction compared to the scattering length of the underlying two-band interaction. We see that this ratio here is very small. So one expects the polar effects not to be important at all. And that's what happens in rubidium-87. There are no significant dipolar effects. Well, when you go to chromium-52, then this improves a little bit, but still it's small. So you can see effects, dipolar effects, but it's very dirty, the system, because it's mixed with other kinds of interactions. However, when you move to electric dipoles, things is very different. So you see that this factor is 20, 36, 240. So there is big hope on the fact that if one managed to build a system of electric dipoles, mostly with polar molecules, then the polar effects will be seen in a much better way. However, the problem is that nowadays those systems have lots of troubles in the sense that the polar molecules tend to react chemically, and then the system is difficult to bring it to a quantum degenerate state. So this is work for the experimentalists, but somehow they feel like this is going to be done in the near future.
Is A the scattering length there? Or the last symbol on the right side, A.
Which one? A.
Right there, where your pointer is.
This would be the scattering length of the two-band interaction, because we are
zero field or something.
Yeah. Okay, now in real systems, as we said before, the dipolar interaction coexists with two-band interaction. And that makes, most of the time, or in many situations, that makes things not that clear with respect to dipolar effects. You see, typically, the dipolar interaction is very long range, so in that sense is supposed to overcome the effect of any possible van der Waals tail. But at short distances, usually, you have a hard core that changes the behavior near the origin of the system. Okay? But still, the important thing here is that it's long range, at least in 3D, which means that at large distances, low densities, where particles are well separated one from each other, you see the effect in the tail.
Actually, this is a little different than the condensed matter definition, because there we say long range means something that gets more important the farther you are apart, like a Coulomb interaction, because the integral diverges. This is just marginal in 3D, but actually it's not even marginal because of the angular dependence, right? It's actually what we would call a short-range interaction.
Well, not only this, if you calculate the potential energy per particle diverges with 1/3 in 3D.
It diverges, but once you consider, but you're going to do the experiments eventually in 2D, and so it wouldn't diverge.
Yeah, that's it.
Right.
Yeah. That's
and
it.
if you consider averaging over angles in 3D, I think it wouldn't diverge either, right?
That depends on the situation. For instance, the kind of systems that we're going to analyze is where you polarize all dipoles. So if things are polarized, then the average over angles disappears.
It does?
Okay, let me tell you more or less. Okay, so, well, regarding the interaction itself, the anisotropy, here I can show you a very simplistic plot of how the interaction that I have shown before changes depending on the orientation. So when you have two parallel dipoles like that, the interaction is fully repulsive, 1/3, as I have said before. But if one is pointing in one direction and the other is pointing in the opposite direction, then the interaction becomes fully attractive. And since we are talking about bosons, if there is nothing that no hard core in the system, then nothing prevents collapse. So it's a matter of stability. Yeah. Also, if I put dipoles like that, this interaction, so head to tail is attractive, but it's twice as attractive as before. And if we put them in front of each other like that, then it becomes repulsive, also with a factor of 2. So you see that the orientation in the system is really relevant in that sense. Okay, also the dimensionality of the system matters quite a lot. So if you're talking about dipoles in 3D, there is the possibility, polarized dipoles, always think about polarized system, fully polarized. So the possibility that one dipole goes like that and the other moves in that direction, so brings in attractive components. And there is a certain critical angle of 54 degrees up to which the system is stable. So otherwise, if you surpass that angle, then the attractive components make the system fully unstable, and that breaks. If you do the same thing, or you analyze the system of dipoles in one dimension, and you tilt, you polarize all the dipoles, but tilt them, then the thing is different, because when they are fully polarized, the change induced by this angle is no more than a renormalization of the dipolar moment itself. So in 1D, you can understand the physics of fully polarized tilt dipoles from the physics of dipoles which are perpendicular to the line where they move. It's only just a normalization. Okay? So things change a little bit with dimensions. If you go to 2D, which is the case that we have been analyzing in our work, the things is once again slightly different. You can polarize the system along a direction that is not perpendicular to the moving plane, so they are tilted. But since this angle is constant, you work out a little bit the interaction, and what you see is that there is a parameter here, lambda, which is the sine of this angle, that somehow can tune the anisotropy. So if lambda is equal 0, so they are moving perpendicular to the plane, there is no anisotropy. The interaction is 1/3, and that's it. If lambda starts increasing because you are increasing the tilting angle, then the anisotropy effects take place. But you can, in a fully polarized system, you can always use lambda somehow as an expansion parameter if you want to find analytical solutions for a problem. And that is what we are done in this work. Since we are studying dipoles, tilt dipoles, moving in the 2D plane, we want to do a many-body description of the system.
Anisotropy here means that you have an arbitrary rotation around the axis?
Well, you put an electric field that polarizes everything like that. So that's a kind of experiment. Okay. So in practice, I will tell you later, in practice, for instance, when you work with magnetic systems, you do that, what you say. So there is some sort of rotation, but if the rotating speed is very high, so if, well, I don't know.
The direction is fixed, that's what I mean.
Yeah, I put an electric field and that direction.
Both angles are fixed. There's two angles,
yes.
right? That's what you mean?
Yes.
Both alpha and the other one, the phi angle.
No, this is not fixed, because I'm supposed to have
Theta.
dipoles moving on the plane. So they can move, but the polarization angle is fixed. Okay, so that's the. Well, what I was saying is that with this alpha fixed, then the expression of the interaction is this one. So here, lambda is the sine of the polarization angle, and you can, for fully polarized system, you can use that as an expansion parameter in order to build a solution for the system, which is the kind of thing that I want to do next. But before that, I wanted to show you something about experiments, because this is not only about theory, but also about experiments. So this is taken from the original paper by Lahai and Fau, I think, Nature 2007, where they first show that under certain conditions you can see anisotropy in chromium. The effect of the anisotropy in dipolar systems But for chromium, which we said before that the strength of the dipolar interaction is small compared to the scattering length of the system, still you can do that. You can see the effects by going close to a phase-back resonance. So in a phase-back resonance, when you move close to a phase-back resonance, the scattering length of the interaction is essentially, or can be written essentially like that. This is the background scattering length, which would be the scattering length of the tubal interaction when you are far from the phase-back resonance, times 1 minus, okay, this is the width of the resonance, and this is B minus the resonant field. So typically you go to the phase-back, you are at the phase-back resonance when B equals B0, so the scattering length diverges. But what they did in that work was not doing so, but getting close to the situation where B minus B0 equals delta. So the scattering length of the tubal interaction drops to 0, and so the ratio of the dipolar length to the scattering length increases, so the effects of the dipolar interaction or the anisotropy induced by the dipolar interaction is better seen. And this is somehow the kind of thing that they represent in that picture here. So this situation, this is for a cloud of chromium 52 atoms, quite far from the resonance. You see that the width of the resonance is 1.7 Gauss. Here we have B minus B0 9, so we are quite far away. The two-body effect, so the hard core and the line hard core in the system dominates. You don't see the dipolar effects at all, so the system is essentially showing you a cloud which is isotropic, spherically symmetric. When you start approaching the region where B minus B0 equals delta, then the system starts showing you that there is some anisotropy. When you are very close to that, you see that the width of the resonance is 1.7, so here it's 2. When you're very close, you clearly see a cloud which is deformed due to the anisotropy effect. So that was the way in which the authors showed that the polar interaction is important, that the polar interaction can be seen.
Does it mean it's taken after the free expansion?
Yes, that's typical. Okay, in practice, and this is, I think, going close to what you were saying, the dipolar interaction can be done for magnetic and for electric systems, or is realized for magnetic and electric systems in different ways, and also due to the engineering that people is nowadays able to do with experiments, they can change different aspects of the interaction. For instance, in magnetic systems, what they do is, as you said before, they can use a static magnetic field that more or less gives the polarization direction, and then a fastly rotating magnetic field in the opposite direction, in the orthogonal direction, such that the dipolar moment can rotate. It does some sort of precession. But if the rotation is fast enough not to excite internal degrees of freedom of the system, it turns out that the dipolar moment in the end becomes something which has this component along this line, and also something that is rotating and is moderated by this sinus of phi, where phi is the ratio of the amplitudes of the magnetic field in this perpendicular direction and the field that is producing the rotation. Okay, so once you work out this dipolar moment into you put that into the expression of the polar interaction, what you see is that on the average, the dipolar interaction is the thing that we saw before, but multiplied by something which is this average over time of this field, of the rotating field, which is in the end giving you something like 3 cosine squared phi minus 1/2. So this quantity, depending on phi, which is, as I said, determined by the ratio between the two fields that we are using, can go from -1/2 to 1. So in that sense, you can tune the strength of the interaction and also the sign. That's what the kind of things they can do. This is for magnetic system. For electric system, well, things is a little bit different because with polar molecules, the internal degrees of freedom of the molecules come into play, and when you put a polarization field, then the field itself somehow makes the different internal states of the molecule couple, and that is good in the sense that the net effect of that, not ask me exactly why because I don't know, but this the experimentalists know, the net effect of that is the dipolar moment is increased a lot, and that's the origin of the numbers I showed you in the first slide, where they say that the dipolar effects in the molecules are very important. However, the problem is that when you do that, it looks like it's not only that you increase the dipolar effect, but also you change the effective interaction between the molecules, and then there are problems to make the system stable. It looks like that the best way to stabilize the system is to confine it in the z direction such that they move essentially in a quasi-2D plane. And that's the reason why we have decided to analyze these dipoles in 2 dimensions, because that's the geometry in which the system looks like it's more stable. So in the end, what we are doing is describing a system of dipoles moving in 2D.
The internal rotate, these are just the standard rotation degrees of freedom of the molecule, nothing more?
Well, there are also vibrational states, but it looks like what the external field couples are the different rotational states of internal rotational state. That's what they claim.
You don't have those in your Hamiltonian?
No. Well, they are put here. So that's part of the magic when I said that in the end you get some sort of effective interaction that it's inducing a large dipolar moment, but it's because of the coupling of
this
the
interaction is between the
Does this describes the internal degrees of freedom of the molecule?
Well, that's internal.
Internal degrees of freedom. Okay, but the electric field couples to the internal degrees of freedom and enhances the dipolar interaction, and also the effective interaction between the molecules. So it's a slightly.
Don't they select a certain internal state?
Yeah, they do. They can do.
So they have a pure. Otherwise, it would leave the trap or something. Or
well, in the end, that's what they do. So they confine the system in 2D just to trap it and avoid somehow collapse or something like that. Because also there are lots of problems. So with this mechanism, it's not only that you enhance the dipolar interaction, but also modify the two-bar interaction between the molecules, and there are problems of chemical reactions between the system. And this is essentially the most important problem they had to fight, that the experimentalists hope to observe very large dipolar effects in a Bose gas in the quantum regime, but they cannot build it because it essentially collapses.
Are these just linear molecules? Are these linear molecules, or are they?
Rubidium cesium molecules.
they're mostly diatomic.
Yeah.
They're mostly, okay. Because
I think.
I mean, if you have, the problems get worse if you have more.
Yeah, that's right. I think that.
Yeah, the problem is very it's very
already
important.
hard with
So,
linear, okay.
so it's a strong problem for them to nowadays there has been no realization of a Bose condensate. So they manage to build the molecules, but whenever they want to bring it to the quantum degeneracy state, at once the system breaks. So they are working on that. But this is experimental. So, okay. So from the theoretical point of view, what we wanted to do in this low regime system was to try to see if somehow the equation of state of this system also satisfies universal properties, as you know, that are satisfying standard two-body interactions brought to this very low density limit. So the equation of state of isotropic short-range interactions is universal in the sense that the only thing that matters in the very low density regime, in the description of the system, the only thing that matters is the scattering length. So there is a universal parameter, which is density times the scattering length to the power of the dimensionality of the system we are analyzing. And all properties depend only on that parameter. Okay? So now we were wondering if that is also the case for the dipoles, taking into account that the interaction is not that short range, and taking into account that you have anisotropy. So first of all, that was the main idea of the study that we wanted to do. Okay, for that, the idea was to use diffusion Monte Carlo, otherwise I wouldn't be here explaining you anything about that. And here, well, I don't think I have to tell you what diffusion Monte Carlo is, okay? But the only thing I want to say is that in the calculations we used a representation of the propagator, which is second order. And this is one of the propagators that has been developed by Xiu Qin from Texas University. And that in any case, the simulation itself needs a guiding wave function to work, okay? So at the very beginning, we thought that that was absolutely simple to do. You just use a Jastrow wave function using, I don't know, the zero energy solution of the two-body problem for the isotropic case, and then you could let the diffusion Monte Carlo bring in all the anisotropy through the potential in the...
Could you explain again about the anisotropic? Because are the angles going to be fixed or not?
There is the polarization angle, which is fixed, but particles in 2D can move around. So it's a gas of particles moving in 2D with a dipolar moment, all of them pointing like that. So this angle with respect to the normal is fixed.
In the plane, it depends on...
Exactly. It's a gas in the plane. Okay. But with the polarization angle fixed. So what I was saying is that for doing the Monte Carlo calculation, we needed this trial wave function. And in order to build the trial wave function, well, we thought that we could do it easily using, for instance, the unpolarized solution of the two-body problem at zero energy.
Why wouldn't you just solve the two-body problem with the angular?
That's what I'm going to say. So what I was trying to reach that point.
Okay.
So because okay, in any case, we tried that using the easiest solution, and that failed because you know that one thing that is important in Monte Carlo is to have a good description of the wave function close to the core. Otherwise, you could get very large sigmas, no, very large variance. Yeah, and since the interaction is anisotropic, then you cannot fulfill with the isotropic solution all those conditions in all directions. So you have to build somehow a solution that incorporates the anisotropy, and that is exactly what we wanted to do here. And okay, this is a little bit boring, so I will try to do it fast. So we started with the zero energy solution we had of the two-body problem. The plan was to solve that, including the angular dependence, all the angular dependence. And once you have the zero energy solution of the problem, then you build a Jastrow factor from that, and then put that into the Monte Carlo and see what happens. So for that, this is very standard. You have to do a partial wave expansion of the solution. In this problem, since the interaction is anisotropic, then the Hamiltonian and the angular momentum don't commute anymore, so you have to be a little bit careful. What one does anyway is to use a basis of the angular momentum in 2D, which is cosine and sine, and due to the reflection symmetry along the polarization plane, you can discard the sine solution, and also to make it for bosons, you end up with a solution that only contains even modes. Okay, you fit that now into the Hamiltonian and check an equation for every different angular momentum state, and what you find is that this equation fulfilled by every single mode is a Bessel equation, essentially. It's a modified Bessel equation. So you can solve it. The solution has a K and an A, which are the two independent solutions of the modified Bessel equation, and you can discard these A terms because they do not fulfill the boundary condition that at the origin psi should be 0. So now you're done. You know that the solution should be this one. Okay? The way in which you can then build, or we have built the solution of the problem, was to split the Schrödinger equation, putting the part which has the anisotropy to the right of the equation, and then building a Green function for the system. Since you know the solution for lambda equals 0, which is the previous one that you have, you can build exactly the Green function, and from that you use an iteration scheme and start doing all the different orders till you get convergence. Okay, that's what we did. Well, here is the expansion, the Green function, and put into the expansion. And the nice thing that one has to one can see from here is that if you already at first order in the expansion parameter, when you do that, when you put here this solution, the solution corresponding to lambda equals 0, start iterating the process to get lambda square, lambda 4 terms. Already at the lambda square term, you see that the interaction, the anisotropy appears, because this term is isotropic, but then you have cosines from the cosine square 1 plus cosine 2, and terms here, and you see that integrals with two cosines are diagonal. So this term here, which is m equals 0, and this term here, which is m equals 0, gives some dressing of the lambda equals 0 solution for m equals 0. But also, to order lambda square, there is this cosine 2 theta, which couples with cosine with m equal 2. So you see that to order lambda square, there is some dressing from the anisotropy. So you start from a solution which was only isotropic, and you get dressing of the isotropic part, but also some part which is anisotropic. Okay. Okay, you can keep doing this scheme. That put second solution back here, and then you have integrals with 3 cosines. So integrals with 2 cosines are diagonal, but integrals with 3 cosines couple states m to states m plus minus 2. So what you see in the end, doing all this game, is that you start from a solution which only has m equals 0 contribution to order lambda 0, which is what you would expect, because lambda 0 is essentially no lambda, which means that all dipoles are perpendicular to the plane, so fully isotropic. And then to order lambda square, you get contributions from dressing of the lambda of the m equals 0 mode, but also you have second mode contributions. If you keep doing this, this term here does some dressing to order 0, to mode 0 and to mode 2, but this guy here gives you dressing to mode 0, mode 2, and some dressing to mode 4. So you start to see. So somehow what you see from here is that different orders in lambda bring in different contributions of different modes. So in the end, since you should somehow sum all the terms in the series, you would have started from a system that has only isotropic solution, and end up with a system that has contribution from all partial waves. Okay. Okay, so this is the analytical part, but in the end, what do you get out from here? So how important are those modes in the solution? Well, that's what we try to show here. So I've taken this polarization angle. This is 0.6 radians, which is very close to the critical angle I was telling you about that would produce collapse. So the largest the angle is, you would expect the more important the anisotropy effects to be. Okay, so that's the reason why we just try to show one of the largest possible angles we can calculate. And what you see here is that this is the contribution of the 0 mode, this is the contribution of the m equal 2 mode, this is the contribution of the m equal 4 mode. So you see that all this stuff about anisotropy, it's important, but in the end, you can survive with only 2 modes, because the contribution are larger, of larger modes is not that relevant. You see that.
Is this verified by, say, variational calculations?
Yes. Yes. Because this is, okay, this is only part of the game in the sense that this is the solution of the two-body problem. But you know that when you go and build a Jastrow factor, it's not only the two-body problem that you have to put in, because in the system there are phonons. So somehow this picture tells you that only the first modes are important, but you should moderate that with the fact that in the end you have to put phonons which will change the behavior, for instance, of this mode here. So it's a game. This has to be checked in the end. One of the things that is important from here is that somehow we can recover an expression for the scattering length, because I told you before that what we wanted to do was to analyze scaling properties of the energy property of equation of state at low densities, and for that you need the gas parameter, and the gas parameter is density times scattering length squared in this system. Okay, so you need to know the scattering length, and the scattering length of the interaction changes with the polarization angle because the interaction itself changes. So we wanted to decide we needed to decide what the scattering length of the interaction is as a function of the polarizing angle. And for that, what we did is go back to the original equation for the zero mode, at order lambda square only, truncated the equation, stay at order lambda square. Now we know from the previous slide that at large distances, which is where you see the scattering length, the second mode is much smaller than the first mode, so what you can do is simple approximation of removing this term. And then if you do that, you get an equation only for the zero mode, which can be solved easily, and because once again, it's the same kind of equation that you find for lambda equals 0, so it's a Bessel equation, and in the end, you solve it, and you get an expression for the scattering length. So comparing what you get to what is the asymptotic expansion of the zero energy solution of the two-body problem in 2D, in general, you get an expression for the scattering length, which is this one. Okay? Of course, this is not an exact expression in the sense that we have been truncating the equation itself, but could provide a good insight on how the scattering length varies. And, okay, we have it here. So what we plot here is this blue line, which corresponds to this approximation expression for the scattering length, compared to a numerical solution of the Schrödinger equation when you get the exact, somehow numerically exact scattering length. And what you see is that the expression itself for the scattering length is essentially good enough. Okay, you don't need to go beyond that. So this turns out to be a very good approximation for the scattering length of the polar interaction with as a function of the polarization angle. Okay, now once we have all that, we can do what we wanted to do, which is do the many-body problem, and using the diffusion Monte Carlo, and check if the equation of the state of the system is universal or not. When I tell you about universal equation of state, I'm talking about things like that. So the energy per particle renormalized, well, multiplied by the scattering length square and h bar and blah, 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 is at the mean field level universal in the sense that it's 4 pi x over the absolute value of log x. Okay, this has to be taken with very caution because in 2D things are much more complicated than in 3D in the sense that the scattering amplitude diverges logarithmically. So it's not clear that the corrections that go after that are small because it's 2D is a world of logarithms. Okay, and in that sense, for instance, Gregory knows very nicely that there are many corrections which are important. So it's not only that you can state with the mean field term, which is only valid at ridiculously small values of the density, but you have to go beyond mean field. But this has been done. This has been studied for different interactions. What would be the corrections after the mean field level? Okay. So what we wanted to see is if the equation of state for dipoles follows some sort of law like that, or incorporating beyond mean field effects that also depend in X, if it's still universal, if it's not universal, what is the effect of the anisotropy? Because, you know, as we have seen, so keeping the gas parameter constant, so for a given value of x, and changing the polarization angle, since you change the scattering length, you also have to change the density. So it's a game, no? It's keeping x fixed means playing with two parameters. So we wanted to see if universality is still recovered or not up to that. Okay, so we want to do that. We will use the Monte Carlo, and for that we will use the two-body solution we have found before, but incorporating effects of induced by the many-body problem itself. For instance, phonons. You have to put phonons. You cannot live simply with the fact that you use the two-body solution. For that, in order to see if our wave function was, or if we can build a simple wave function that can be used in the Monte Carlo, what we did was to compare the solution of the two-body problem matched with some phonons at large distance with what you would get if you solve the many-body problem using the hypernetted chain equations, optimizing the correlation factor in the way that, for instance, Professor Eckhart-Kroczek is doing. Okay, so somehow we used we performed variational calculations using the matching point between our solution and the phonon behavior, the matching point using that as a variational parameter, and so that you can get perfect agreement. So what you could do from H and C, can be reproduced very nicely using the two-body solution matched with phonons. So that was the plan. The plan of the story was, in the end, to use this two-body solution matched with phonons. And here I show, well, what is the two-body solution, the Jastrow factor that we get in one direction, which is the parallel direction where all dipoles are pointing like that, and the other is in the perpendicular direction where they are pointing like that. Okay, and in between, okay, you can do all the matching with the cosine terms. So now we have the wave function that you can use. We have everything ready.
Just to understand, so the hypernetted chain solution is a kind of interpolation between the exact solution at short distance and phonons at long distance.
It provides you the best Jastrow factor for the many-body problem. It best constrained to the kind of things you are putting into H and C, because H and C is not like Monte Carlo, it's not exact. Okay, H and C is more like adding diagrams.
Here in the plot, they say that there is very good agreement with the solution at short distance.
Yeah, but look at this. Look at this. The plot is it's a little tricky. So you have to match. So a short distance is very good with the two-body problem, and the H and C is giving you essentially exactly the same thing. But at large distances, the differences start to appear. But of course, I have cut the plot at the point I want.
Probably at low density, it's a very good theory, right?
Very good. H and C is very good. We could have done all this work with H and C, but we prefer to use Monte Carlo because, H and C is the Monte, so you cannot sell it. the Monte, it's old-fashioned. No, you cannot sell it properly. Okay. Okay. Anyway, so now we have everything ready, and to do that, and we just go and calculate the equation of state, and what we get is this. This is the result for the equation of state of the system, where here what I plot is the energy of the system divided by the mean field solution, this 4 pi x over log x, for different values of polarization angle, and compare to the equation of state that incorporates beyond mean field effects, which has been obtained by essentially Gregory in one of his papers. So this is supposed to be the equation, the universal equation of state incorporating beyond mean field effects. For the sake of comparison, I have included results for it's hard spheres, but it should be hard disks in 2D, where you see that hard disks follow quite nicely the equation itself. But dipoles do a different thing. Okay, dipoles prefer to stay close to the mean field term rather than to the beyond mean field approximation. Okay, but the interesting thing is that you see that all points for different polarization angles seem to be one on top of each other. So somehow the conclusion is that dipoles do not fulfill the universal curve, but they tend to scale among themselves.
So the beyond mean field, that's the Monte Carlo calculation, or?
This guy here can answer.
So is that a Monte Carlo calculation?
No, the idea is
But this, say like that, it sounds very nice, but it's a mess, because as we said before, in 2D, you have logarithmic divergences already in the definition of the scattering amplitude, so everything becomes much more complicated. And actually, there are, I don't know, how many different approximations did you collect for that? I think about 20? I don't know. So there are as many theories as flavors. So.
In 3 dimensions, this would be similar to having the mean field, which means that the chemical potential is linear with the density. And beyond mean field, okay, some different powers, sensitivity with the density to the 3 powers. And this is just 2-dimensional analog.
Okay, so in any case, the thing is that what you see here, as I said before, is that dipoles follow their own law, but they all follow independently of the, properly scaled, they all follow independently of the polarization angle. So somehow they are universal among themselves, but not with the curve. Okay, so that was the main result of this part of the work. Here I have included, just for the sake of, so you can see, contributions or the representation of a pair distribution function for different densities and along different directions, no? R0, so x direction, y direction. Okay, at very low densities, where you see the polar effects are small. Intermediate densities, you see that the difference between one and the other curve can start to be large. That for the pair distribution function. And also we have same thing or similar things for the static structure factor, where you see that differences are more apparent. So the conditions are the same, alpha, for instance, 0.6, density 16 in these dipolar units, but here you see that the differences are more apparent. This is DMC, all of this is DMC. Okay, also the final part of that was to try to evaluate the one-body density matrix, but you know, in DMC is not pure, but anyway, we calculated that, and the condensate fraction from the limiting value of the one-body density matrix, and you see, and that we compare to the Bogoliubov, which is supposed to be universal prediction in 2D, and remarkably, the condensate fraction seems to follow very nicely the Bogoliubov approximation for different values. Okay, so that was the part regarding the low density regime. Now, I would like to move a little bit onto the high density limit and explain a little bit what can be interesting at high density. So of course, at high densities, particles are close to each other, much more close to each other. So you would expect that the effect of the anisotropy could be seen in more places. And this is exactly what happens. For instance, here, this is a plot I show, a slide I show from a paper by Levenstein, Sliapnikov, and Santos, where they studied the spectrum of elementary excitations for dipoles on a pancake. Okay, I plotted like that, so I represented like that. But in the in fact, what they did was to analyze a system where it was infinitely large along the plane and confined only in the z direction using Gross-Pitagevsky equation. But what they found is that depending on the ratio of the effective dipolar coupling constant, which they define as essentially proportional to the square of the dipolar moment, and the coupling constant of a short range interaction that they put, they see that the spectrum of elementary excitation can change quite a lot. And even though the system is very dilute, or the system they studied was dilute, you could start seeing large effects like a Roton here. Roton, which is typically from systems, or at least I'm used to see that at very much more correlated systems like helium-4, for instance. Okay, but this is a dilute system, and this is induced by the anisotropy.
Looking at the picture, all the dipoles are pointed vertically.
Yeah, this is not exactly what we are doing. So this is the experiment, the work that they did, where they analyzed the effects of the anisotropy on a pancake. Okay, so you can polarize all the dipoles in the direction perpendicular to the pancake, but if you open the pancake a little bit, then you can have the anisotropy because they are pointing like that. So it's a different system as the one we are studying, but still it tells you that the anisotropy effects can appear in many different situations and can induce strange things like the behavior like that.
So it's attractive in that direction.
Somehow, so we don't have this geometry, but in the system that we are analyzing, when you tilt the dipoles into D, you are doing similar things. Because if you tilt the dipoles, so I put two dipoles like that, this is fully repulsive 1 over R3. But they put it like that, and this is 1 minus 3 lambda square over R cubed. So I'm reducing the strength of the interaction. So somehow it's similar, that depending on the orientation, you can see the anisotropy. In that system, in the end, it's similar because you can put two dipoles like that, they are fully repulsive. You can put it like that, they are less repulsive, but you cannot put one on top of each other because the system collapses. So it's always repulsion, but it's weaker in one direction, stronger in the other.
Imagine an actual phonon where it went like this. Right? Is that what that is? Where there's an actual, they call it buckling instability on surfaces, right?
Yeah. Similar. So they talk about Rotan instability because of that. So when you start opening the pancake and you permit lipos going like that, then this instability appears. So it's somehow related. Okay? So that induces us to think that maybe it would be a nice place to look for anisotropic effects at the excitation spectrum, dynamic excitation spectrum. So we decided to do a calculation of the response function for our system and to try to see if we could see similar effects as those ones, but in our system. If we can find the Rotan, and that Rotan depends on lambda. And if it becomes deeper when you increase lambda because the anisotropic effects are more important or what. Okay, for that, we just use CBF. CBF is an old theory developed in the correlated basis function, CBF. It's an old theory developed, I think, in 1967 by Campbell and maybe Finberg itself. Chang and Campbell. And it's based on the idea that it's a linear response. So you have your system, you put an external perturbation, that weak external perturbation, that external perturbation induces a change in the density, and the ratio of this change in the density to the external perturbation essentially gives you the response of the system. Then what you do is build in the framework of this correlated basis function, you build some sort of wave function which is supposed to be the exact wave function of the system. Well, this is a trivial time exponential. And here, what one puts is some sort of, is the exponential of the sum of different one-body terms, two-body terms, which are supposed to be time-dependent and reflect the effect of this perturbation that you're putting there. Okay? Then, with this wave function, you build the action, minimize it, and depending on what level of the theory you stop, you get one thing or you get another. For instance, if you do the optimization just by keeping only the first term, you go all the way down to this Feynman spectrum. So by keeping only one body terms, you recover a Feynman spectrum where the S of k and omega is represented by a single line of long-lived excitations, which are k squared over, 2m S of k, which is missing here. So it's k squared over S of k. If you go beyond that and include the second order term, what you get is that those Feynman phonons can interact between themselves and end up with an expression of the density response, which is like this. No, this is a typical structure of a propagator with a self energy, which has this form here. Well, okay, this is all terms, some things which are nasty to look at, but the important thing to notice here is that the self energy that you get here is essentially, looks like very much what you would get in second order perturbation theory, starting from a basis of Feynman phonons that you use here, and with a matrix element which depends only on S of k. Okay? So you can get, at this level, a good approximation of the response function of the system by starting only from S of k. So the plan was to get S of k doing the Monte Carlo thing and plug that into those expressions and recover the prediction for the density response. You do that for 0 angle, which is no polarization, lambda equals 0, and you see that, okay, nothing very surprising in the sense that here you see the Feynman spectrum, low density. As you start increasing the density, then you see a roton. Okay, but this roton is induced by the density. It's nothing like the anisotropy, because here we don't have any kind of anisotropy. So it's just like in helium-4, nothing more than that.
So the points, the green points are your...
No, green points are Feynman spectrum.
All right.
And all these are color maps of what you get in CBF. So CBF is not only giving you a line, it's giving you the line of elementary excitations and a background signal coming from the interaction between the different excitations. Okay, so that goes beyond the Feynman approximation. But you know, this is...
But they come from the same ingredient, I mean, just
for
computing S of k?
From S of k, so the idea is from S of k,
yes.
you get this guy, this one, put it here,
Oh,
the other
okay.
interaction,
Yes.
yeah,
Okay.
okay. No, but there is no iteration. S of k goes here, from here to here. Here, do put that here, evaluate this integral, fit here, and you're done. Okay, so it's something like 5 minutes running the code and 10 months writing it. Okay, so here what we saw, what I was telling you is that what we saw was the standard thing of what you would get in condensed matter like helium, no? That you increase the density and a roton appears, but nothing related to the anisotropy. Okay. Okay, then our colleagues in Austria decided to do a fast analysis of the system, doing H&C calculations, and looking at the stability of the system once you put back the anisotropy. Now we restore the anisotropy, so we don't set lambda equals 0, we put lambda something between 0 and 0.61 radians, which is the critical angle, and then try to look for the stability of the H&C solutions. And well, there is an old work by Castillejos which tells you that one way of looking at the stability of the solutions in H&C is to evaluate the lowest eigenvalue of the Hessian, of the energy as a function of the G of R, and if that eigenvalue becomes non-positive, then the system is unstable. So one way to check for system instabilities in H&C is to look at this. You look at the eigenvalues of the system and see if it gets positive or negative. So in all those conditions, no, density 6, 32, 128, you see that the system is always stable up to the critical angle because that never becomes negative. But when you go to 256, you cannot reach the critical angle because you just stop having solutions before that. That means that at this level, you find that the system is not stable anymore. So with the density and the critical angle, the system can become stable. So
if you're saying, so your eigenvalue is still okay here, is that what it is?
Yeah.
But H&C equations don't have a solution.
No, up to here you have always solutions. Up to here you have always solutions. But when you go here, you don't find any solution. So the last solution that we found was this one. Starting from there.
Well, okay, I'm not understanding clearly what you mean by that. So you put in.
The H&C iteration never stops; it really blows up in the end.
Okay.
So you calculate two things.
I've done my PhD thesis was on H&C, so I mean I think.
You can tell me.
So I'm just trying to understand. So this could just be the elementary diagrams that are left out of H&C are not there. If you did a Monte Carlo calculation, you could get an answer. If you can get an answer for a Monte Carlo calculation, then the problem is that the H&C equation.
This is next, exactly.
Okay.
So the only thing I was saying is that agency at this point shows that optimized agency is not able to find a solution anymore. That's the only thing I was trying to claim.
But if it doesn't find a solution, that does not mean it collapses. That could just be
Whatever it is. It could be whatever it is. Agency is an approximation, and also this is agency 0. So you know that by not including elementary diagrams, things get worse. And if you increase the density and go close to instability, it's getting worse and worse. So that was only an indication that something is happening, but not. It's only qualitative, not quantitative indication. That was the only.
Has agency been able to ever get a solidification density correct?
No, not really. Not correct in the sense you would expect in Monte Carlo.
Well, I mean, within, say, 10% or something.
Well, more or less, about 10%, yes. In helium-4, for instance.
I didn't realize that.
Okay, so since we know all the problems that you were pointing out about agency, then we decided to try to see if we could see anything like that in the doing Monte Carlo. And for that, so the problem is that we are going to high density, so we don't want to use anymore the two-body solution of the zero energy two-body solution, because that works for dilute systems only. And we had to do something better. And along this line, we decided at that point that the easiest thing was to do a path integral ground state calculation, because in that sense, path integral ground state is more forbidding in the sense that you can put something reasonable as a trial wave function at the endpoints, but then the propagators themselves will improve and let you get all the things that you have not put by hand on the trial wave function. So we cannot use the two-body solution. We don't have any agency solution, so we tried peaks. And the peaks that we tried was using at the endpoints of the chain the isotropic solution, the lambda equals 0 solution. Okay. Well, the only thing that I shall mention about this peak calculation that we did is that we use a fourth order propagator, which is one of the family of propagators that Siu-Chin derived. And we found that the one that he calls ACB works, for that problem at least works great, in the sense that it's easy, convergence is fast, and okay. The only thing that you have to worry about is this term, which has this dressed interaction here, which is the potential plus something which is proportional to nabla of the potential square. So you have to take a little bit care of that. But out of this, it's a standard path integral calculation. And we did that, and what we got was this. Here I show the static extractor factor and one snapshot of the system. Okay, here this is the case of alpha equals 0, so fully isotropic for a density of 128. So it's a gas. And the same down here I show the for alpha equal 0.58, which is close to the critical angle, but half the density. We see that the component in one direction, the component in the other direction of the static extractor factor is quite different. So the system is no longer isotropic, and you see that clearly on the static extractor factor. But still, this snapshot that I show here is for this case. So I knew that was going to be a gas. But what about this? Well, this is essentially gas. Huh? Then you start increasing the density, and you see that the static extractor factor develops a peak in the y direction, which starts to be large, and the system is doesn't look like as a gas as before. And if you keep increasing that, what you see is that at a larger density, there is a huge peak here, and the system goes to lines. So what you see is that the system changes in the structure. It goes to what it's called stripe phase, because the system forms stripes. If you do a plot of that in 3D just to see how it looks like the static extractor factor in all directions, not only x and y, you see that it's always well peaked in the y direction. So in this other direction, it looks like a standard fluid, but in that direction, it has a strong peak.
Why doesn't it go into like a square lattice instead of just a stripe? Is there some simple geometrical reason?
Well,
It doesn't develop a density wave in the other direction.
next. Okay, so this is the Fourier transform of the static structure factor, and you see that on one density it looks like pretty isotropic in the sense that at large distances it goes to 1, but in these conditions with we saw the stripes, it really produces density wave, as you were saying. So you see that there is a change in the system property. It goes from the homogeneous gas to an anisotropic system with a straight face. Okay.
Snapshot didn't show that. Was that just because?
No, but that was one snapshot. So it's not the average of anything, because the density of the system is homogeneous. If I average over everything, then I get something which is. So it was just one picture frame shot, just to see that at every time, in the simulation at least, you get these stripes. So the reason why the stripes form is what I said before, that along one line you have less repulsion than along the other line, along the other direction. So more repulsion here, try to apart one particle from the other, so they keep them in place. While this other interaction here, the interaction along this line, if you approach the critical angle, so 1 minus 3 lambda square, it's close to 0, so the interaction is 1 over R3 with a very small coefficient here. So it can be sort of a fluid along that direction, but it should somehow pack along that direction, and that forms stripes. Which we are not inventing anything, because the stripes have been seen that in Bose-Hubbard models. In Bose-Hubbard models, they do whatever they want, and they get a huge bunch of new phases. And in particular, in Bose-Hubbard models, for dipoles, with dipoles, as a function, well, on the phase diagram, as a function of the ratio between the hopping term and the interaction and on the density, you see here they find this what they call the checkerboard phase, here what they call the star phase, but in between, for filling 1/3, they could see in the 2D square lattice, they could see the stripe phase where the stripes goes in diagonals. Not only for the homogeneous case, but also for the trap system. This is also a simulation solution of the Bose-Hubbard model for the trap system, where they see many different things, but they claim that those lines here correspond to the stripe phase. Okay, I think it's easier to say it like here. So the stripe phase has been previously seen in optical lattices with dipoles. The difference in our case is that we have seen in a continuous system without the need of the optical lattice. Okay, and going back to finishing to the structure factor. You were asking me before if you see anything about this transition in the density response. The answer is yes. We have here for a n equal 128, we do the same CBF calculations starting from the static structure factor that we have evaluated, or we have obtained in this path integral ground state calculation with the full, in that case, with the anisotropic, so including the anisotropy. So you have alpha equal to 2. You see in one direction it goes like that, on the other direction it goes like that. It's not that it's much of a difference, but when you start increasing the polarization angle, then you see that in the y direction the roton becomes more pronounced, and if you keep increasing it, it almost goes to 0. So it's close. It's similar. The physics is similar to what this Sliamnikov and Levenstein were describing, but for that system. Okay, also, so we see that there is a transition. We have seen it explicitly, that the system properties change. We see that in the elementary excitation spectrum, and the fact that this roton goes to 0 somehow tells you that the transition between one phase and the other is not going to be first order, because in first order transitions, for instance, if you go to helium in the solid gas transition, you don't see that the roton approaches 0, okay? Because it's a first order transition and there is some latent hint in game. But here you see that as when you approach the instability, the roton drops to 0. So you're building a density wave, which is what is moderating the shape of the system as we have seen before. This is exactly what you saw here. We used, in order to characterize a little bit how the transition is to the stripe phase, we used the ratio of S of 0k, so along the y direction, and the number of particles, and see that in the situations, for instance, alpha equals 0, when we know that there is no stripe and then the system can only go from gas to solid, which is first order transition, you see that the other parameter jumps. Okay, you get that for alpha equals 0, dot 2, dot 4, and when you increase that, you see a different behavior, a continuous behavior. So everything seems to indicate that this transition going from gas to stripe is not first order, so it's second order. I won't say that it is second order, but it looks like it's second order all the way. Okay, last slide. With all these things, what we could do is to build the phase diagram of the system, and it turns out to be something like this, because this is not yet finished, in the sense that with the jump in the order parameters of k over n that I have shown you before, you can characterize how the system goes from gas to solid. With the continuous lines, you somehow try to decide what the line going from gas to stripe is. And then there is the question of what happens here, because you know, we think that if you keep pressing the system enough, the system will, in the end, depart from the stripe phase and become a solid. Okay, but this is very difficult to see. Our calculations with, let's say, 400, 500 particles show that this line seems to be very steep, in the sense that you see stripes all the way up when you increase the density. But of course, if you use 400 particles and you have to go to a density of 1000, then everything is finite size effect, so because of the simulation box. So that's why I say that my prediction to what we have here is, I don't know.
What kind of a solid is it?
I don't know. I'm saying that I don't know.
Not there, but on the other part, is it rectangular?
Triangular.
Oh, it's triangular.
Yes, it's triangular, but also anisotropic
So
triangular.
there's a little bit of a frustration between.
Yeah, it's triangular because it's 2D, but it's anisotropic in the sense that it's since the interaction is different in one direction from the other, then the triangular lattice that you obtain, the optimal triangular lattice in a variational calculation that you obtain is not 60 degrees. It's not like that.
You're using a rectangular simulation cell?
No. What?
You're using a rectangular simulation cell or a
The triangular. Well,
No, but
Periodic
simulation box.
no, rectangular, no, rectangular.
It's like that.
It's part of the game. No. Yeah, no, I understand, but it's not that easy, because commensurating the box with the lattice that you don't know exactly what it is,
Sure. I
that
understand.
that's part of the.
When we do the things for one over R potential, if you're in the solid phase, it will form a solid very easily, and it just rotates to fit into the box. It won't line up along the axis, but it'll rotate.
But this is isotropic, so 1 over Coulomb.
Yeah.
So the problem that we find here is about finding the commensurate box, because we don't know exactly
You have
what the.
one more constraint, you're saying.
Yes. And we are okay. Look at this. Working.
It seems like it would distort the triangular lattice somehow.
That's what we are using. That's the kind of thing. But trying to optimize how should you distort it.
To understand how much of the distortion might come from the fact that you're constraining the system a little bit.
But you have to do it somehow.
Of course, but I mean,
Could you consider the angle of the tilt to be a variable, so you could
minimize the energy.
Exactly.
Yes.
Mm-hmm.
I You could put these various things into your Hamiltonian.
That's what we are trying to do. It is not finished.
So I missed something really basic. You call it a gas. Do you see superfluidity in
Not really.
But it'd be hard for it not to be a superfluid.
It should be, yeah.
So
It will
then,
be.
if it is, then the transition into stripe, is that superfluid to insulator transition, or is there some super solid phase there where you still have superfluidity, but you start to develop a stripe?
You have superfluidity in one
Yeah.
direction.
Right, you have the,
A
right, along the
condensate
line.
fraction in
But
one
can you,
direction and
so
not in the other.
that.
The condensate fraction, it's
Well,
always.
I don't think so.
In the
The
line.
condensate would be anisotropic, but it would be able to jump over those little,
Yes.
as long as the barriers weren't too big, right?
Yeah,
Mhm.
that's what I would guess.
So if it's global, then is that, so in other words, along the stripes, if there's still connectivity, if there's still,
Yeah.
then you have a kind of a super solid order, right? There's modulation and it's.
So we have not
global.
checked if we have a super solid, but what I can tell you is that on those Bose models that I showed before, they have super solid phase, they have
So
side
that's-
phase, but
that's
they
not-
differentiate one from the
that's-
other.
The super solid phase is more artificial there. You put a lot of, it's much easier to form.
This would be like superconductivity and charge density waves.
Right,
Mhm.
simultaneously,
Yeah.
Could be.
or coexistence.
Honestly, I don't know.
But if you say it's a first order, then it's that would imply that it's.
Yeah,
it's
it
a
looks
better
like first order.
insulator to
Mm.
superfluid transition.
Looks first order.
Yeah, it's got the high transition temperature.
Yeah.
Okay, so I'm done.
temperature.